Welcome to StructureTool2D. In this training, I will walk you through how the app works for three types of two-dimensional structures. We will begin with the default frame example, then we will move to the beam example. Finally, we will look at the truss example. As we go, I will show you how each part of the app fits into the overall workflow. I will start with the frame example because it gives the clearest introduction to what the app reads and how it interprets the main input parameters. Once that foundation is clear, the same logic will be easier to follow in the beam and truss examples. The app is organized as a workflow. In tab A, you load the structure data file and preview the geometry. In tab BC, you run the main analysis, review the graphical output, and access the slope deflection section. In tab DE, you use the unit load method and the force method. So the overall process is simple. First, load the file. Next, check the geometry. Then run the analysis. After that, inspect the results. Finally, move to the method section that matches the structure type. We begin in tab A. This is the starting point of the app. Here, you select the structure data file, then preview the structure geometry. Before running any analysis, always treat the geometry preview as your first quality check. The app should show the structure you intend to analyze. If the geometry is wrong here, the analysis that follows will not be trustworthy. Now let me explain the main categories of data the app reads when the structure Excel file is loaded. First, the structure type tells the app whether the model should be treated as a frame, beam, or a truss. In this first example, the structure type is frame. Next, the counts for nodes, members, supports, and loads tell the app how many rows of each type of information it should read. These counts matter because the app uses them to interpret the rest of the file correctly. The node table defines the geometry. Each node has a node number, an x-coordinate, and a y-coordinate. This is how the app knows where each point is located in the structure. The member table defines connectivity and properties. Each member has a start node and an end node. The member table also provides the section and material properties used in the analysis. These include E, area, and moment of inertia. In the frame example, the member table also includes hinge flags. That matters because hinge settings affect structural behavior, and they also influence which method sections are most suitable later in the app. The support table identifies the restrained nodes and the support type. This is how the app knows where the structure is fixed, pinned, or otherwise restrained. The load table records the external loading. Depending on the load type, the app reads whether the load acts at a node or on a member, together with the necessary magnitude and location information. Keep this central idea in mind. When we move from the frame example to the beam and truss examples, the app is still reading the same core categories of information. Nodes define geometry. Members define connectivity and properties. Supports define restraint. Loads define the applied actions. Now move to tab BC. This tab contains the main analysis controls. In the settings panel, number of elements per member controls the discretization. For the frame example, the default value of 10 is appropriate. The deflected shape magnification factor controls how large the displaced shape appears on the screen. The plot scaling factor controls the size of the M, N, and V diagrams. Because this is a frame, not a truss, leave the truss checkbox clear. Now follow the standard sequence. Open the structure data file if needed. Plot the structure geometry, then click Analyze Structure. Once the run is complete, the results and plotting buttons become active. Now review the frame outputs. Display analysis results opens the numerical output. Display deflected shape shows the displaced frame. Plot M, N, and V diagrams shows the bending moment, axial force, and shear force diagrams. Plot geometry, loads and reactions combines the full problem in one view. For the frame case, this is the main path through the app. Begin with the geometry preview. Then move to the numerical results. Then interpret the diagrams that show the structural response. Now move to tab DE. Because this is a frame, the most relevant method is section E, which is for beam and frame models. In this panel, you choose a target node and direction, then compute either a displacement with the unit load method or a redundant reaction with the force method when the model fits the method assumptions. For the default frame example, the unit load method is the most natural demonstration. You can run the method, see the reported displacement, and compare that value with the general analysis results from tab BC. Before we leave the frame case, let me point out an important feature that also appears in the method sections of the app. In the method-based sections, the app does not stop with an answer on screen. It can also generate report documents. In particular, you will see an analysis report and a summary report associated with these sections. The analysis report is the fuller document. It is meant to preserve the calculation in a more complete form, including the setup, the method steps, and the computed results. The summary report is the shorter document. It gives you a more compact view of the problem classification, the main setup, and the final results. That means you can use the app in two ways at once. You can study the result interactively on screen, and you can also open the reports to review the same method in a more formal written format. Now let us move to the beam example. Return to tab A and select the beam data file. The app now reads a beam model. In the geometry preview, you will see a beam system rather than a frame. This is an important point. The workflow of the app remains the same, but the structure type changes which tools and outputs are most useful. Move again to tab BC. Because this is still a beam or frame model, the truss checkbox remains clear. The main analysis sequence is unchanged. Analyze the structure, then inspect the results and plots. For the beam case, the M, N, and V plots become especially important. You can use them to understand how the beam responds to the applied loads. The deflected shape is also helpful, but in this case, the internal force diagrams usually become the main visual teaching tool. This beam example is also the best place to demonstrate section C, the slope deflection method. In tab BC, section C is specifically labeled for beam and frame models. This section solves continuous beams and rectangular frames using the slope deflection method. So for the beam case, the path through the app is clear. Use tab A to load and preview the beam. Use tab BC to run the standard stiffness analysis. Use the results viewer and the M, N, and V plots to interpret the beam response. Then use section C to demonstrate the slope deflection method on a beam model. Now let me add one more point here. Section C also supports the report workflow. If you generate the reports in this section, the app provides both an analysis report and a summary report for the slope deflection method. The analysis report gives you the fuller record of the method. The summary report gives you the shorter version that highlights the essential result. At this point, you are not limited to the live interface. You can run the method, inspect the result on screen, and then open the reports to review the same work in a document format that is easier to revisit later. After that, you can move to tab DE and use section E again, because section E is for beams and frames. This allows you to compare the main beam analysis, the slope deflection workflow, and the unit load method within the same app. Now let us move to the truss example. Return to tab A and load the truss data file. The app now reads a truss model. In the geometry preview, you will see a truss rather than a beam or frame. Once again, the same core input idea still applies. The app still reads the structure type, the nodes, the members, the supports, and the loads. But the behavior of the model and the most relevant outputs now change because the structure is a truss. Move to tab BC. For the truss case, the key changes are the number of elements, or NE, and the truss setting. By default, the app sets NE equals 1 and selects the structure is a truss checkbox. This is one of the main differences between the truss workflow and the beam or frame workflow. Now run the same basic sequence. Open the structure data file if needed. Plot the structure geometry. Then click Analyze Structure. After the truss analysis is complete, the app emphasizes a different kind of output. The numerical results are still important, but the graphical focus changes. Instead of focusing on M, N, and V diagrams, you should use the truss-specific axial force output. Now move to tab DE. For the truss case, use section D, not section E. Section D is specifically labeled for truss models. In this section, the app lets you compute a displacement at a target node and direction using the unit load method, or compute a redundant support reaction using the force method for a truss model. This gives the truss example its own method-based path through the app. You can run the main truss analysis in tab BC, inspect the axial force output, and then move to section D to apply method-based calculations that are specific to trusses. Here again, the report workflow becomes useful. In the truss method section, the app can produce both an analysis report and a summary report. For the unit load method, these reports help you review the target displacement problem and the resulting calculation in a structured format. For the force method, the reports give you a formal record of the redundant reaction calculation and its result. So as you move through the truss case, you are not only solving the problem, you are also building a written record that can be reviewed, discussed, and compared with the main truss analysis output. As you saw earlier with the beam and frame method sections, the analysis report gives you the fuller calculation record. The summary report gives you the shorter, result-focused version. That makes the report system one of the most useful teaching features in the app. It connects the live interface, the method logic, and the final result in a format that is easy to review after the calculation is complete. At this point, you have seen all three app paths. With the default frame example, the app demonstrates the standard frame workflow, and it gives the clearest way to explain the main input parameters. With the beam example, the app demonstrates beam analysis, force and deformation plots, the slope deflection method section, and the reporting workflow for that method. With the truss example, the app demonstrates truss analysis, truss-specific output, the truss unit load method, the truss force method, and the associated reports. This is the main idea I want you to take from this training. StructureTool2D is more than one solver with one output path. It is a teaching app with a common interface and distinct structural workflows. Work through the app in the order presented in this video, and you will see how to use the main interface, follow each structural workflow, and understand how the app adapts to the type of structure you are analyzing. Thank you for watching.